Welcome, everyone. We're so glad you're here, and I want to introduce Steve Holmes, Application Engineer with Leader. Take it away, Steve.
Thank you very much, Cindy. I want to welcome everybody here today. Appreciate you guys attending. Please, as we go through the presentation, go into the chat window, type in your questions. If you have questions at the end of the session, we will address as many of the questions as we can. If some of the questions are going to take more time or be something I've got to look up, we will address that offline, but please, we will get to every single question that you guys have, and all of your questions will be addressed and answered as we go through this. So please, as we go through this, ask questions. We love the questions. So the question is, what is PTP? So PTP is Precision Time Protocol. It is basically the black burst and tri-level used for uncompressed video and audio used in ST2110 and ST2022-6 video networks. It is a protocol used to synchronize clocks through an IP network based on counting time from an established point in time known as the epoch, or the start of time. And for PTP as well as SMPTE, the start of time is 1970, and that is the International Atomic Time, or TAI. And it is the start when everything happens and when everything counts from that point. So we can know exactly what line you're on, what frame you're in, by counting things from that particular date and time. It is essentially, like I said before, the replacement for black burst and tri-level sync in an IP network. PTP has actually been around for quite some time. It is standardized in IEEE 1588. It's the standard for precision clock synchronization protocol in network measurement controlled systems. The thing that SMPTE has done in 2059-1 and -2 is added the video parameters that did not exist in the original IEEE 1588. So when you use a device, a network switch, or any other types of devices in your network, they need to know about SMPTE 2059. Not all PTP is exactly the same. PTP uses this thing called either the BMC or the BMC-A, just depending on which standard you're coming from, that performs the distributed selection of the best candidate clock, i.e. who is the grandmaster clock. And that's based on clock properties and clock priorities that we'll cover as we go through this whole system here. So to set up a network, a basic super simple network would be a basic PTP island. It can be locked to GPS, or it could actually be locked to existing house. But being locked to GPS is going to give you a much higher clock class, i.e. it's going to be much more stable and closer to the actual GPS lock. It's best if you're going to start a network that you actually lock your PTP source to GPS and then use the black out of that GPS locked grandmaster to lock the rest of your house. Then it's going to go into the network. It's going to go out to what they term as ordinary clocks. Ordinary clocks are all the slaves. And then you can use test equipment like the LV5600 or the 7600 to be able to look at how PTP is behaving through your network and monitor and troubleshoot things. A lot of networks are using a master slave or a redundant PTP source, just like we typically do with Black Burst using a changeover. But with PTP, a changeover is not required. The changing from one master to another master when there is a fault or something changes within the signal class is done with the PTP protocol itself. And I'll talk more about that as we go through the presentation here. In a lot of cases, we are implementing what has become known as the amber and blue networks. So they aren't so much that one's a master, one's a slave. It's just twin networks putting out the same exact material. And 2022-7 then will take that redundant data, bring it into a PTP slave or your end device, and it'll have a packet picker in there that will look at both flows, and it will grab the data from one flow or the other flow and give you a single output. The amber and blue networks are air-gapped except for they need to be able to communicate PTP between the 2 or 3 or 4, however many masters, PTP masters that you have, so that the selection can come about for who is going to be the grandmaster and who's going to be the next succession in line. So the 1588 standard is the one that was originally set many years ago for the IEEE 1588 for PTP. All of the cell towers in cell phone networks are clocked and use PTP. That's how they do handoffs from one cell site to another cell site. And most of the time, we don't even know a cell transitions happen. Once in a while, you get a little click, but most of the time, nothing happens. So then there's the SMPTE 2059-1 and -2 that set up the pieces that are added to the IEEE standard. So SMPTE defines the epoch, the start of time, the same as IEEE 1588 does. It provides alignment points for things going back all the way to analog television. It sets up the 10-field sequence. It sets up the analog high definition, the digital high definition, the UHD parameters that we need. It also gives us the ability to carry time code. All of those pieces do not exist in basic 1588. Those were all added by SMPTE so that now we have the video parameters that we need to be able to do what we do in the video industry. So -2 just further defines some of the profile identification, the best master clock algorithms, how we were going to use it within video realms and slaves, clocks, and the physical requirements that were needed to be able to give us the lock and then be able to walk from one master to the next master when it's needed. So quite often we call the master that is providing the PTP the grandmaster. Then there are subsequent master clocks that are all waiting in line. So if something falters on the grandmaster, the next clocks will walk in. And if it happens at the GPS level, it's a seamless walk from one grandmaster. The secondary unit that's next in line will just pick up and start putting out the same exact point in time. The nice thing, they're all locked to GPS. They're all talking about the same exact point in time. Then we have slave clocks, which is sometimes called ordinary clocks. It is a clock that is going to be synchronized to the grandmaster. And then we have PTP domains, which I'll talk about near the end of the session, that are logical groupings of clocks so that you could actually have something putting out AES 67 or Dante and then also have video PTP going out at the same time. And you can group those by separating them as different domains. So we have several different clock types. The Grandmaster, as I mentioned, is the reference for all other clocks in the network. It is selected by the BMCA, looking at the quality of the clock and the priorities. We have boundary clocks. Boundary clocks, you can almost think of as a reclocking DA. They're going to look at the Grandmaster coming in, and they're going to remaster a new PTP source that is all locked to the Grandmaster. They are very handy and very nice because they actually cut down on the amount of PTP traffic that the Grandmaster actually has to deal with. And we'll look into that a little more in depth. Transparent clocks aren't used nearly as much anymore as they were when PTP started. Transparent clocks just modify the timestamps or put in a timestamp to say how long did it take for the PTP message to come into this clock or this switch and leave the switch, so that the receiver knows how much to modify that to be in lockstep with the Grandmaster. Ordinary clocks are just PTP aware slaves sitting on the ends of the networks. So when you have a network and you have multiple sync sources in there, the BMCA is going to be used to select who is the Grandmaster. Just like when you set up two sync units going into a changeover device, you want to be in control of who is the best Grandmaster and who is the secondary in line. You don't want to leave that to chance. So you need to be able to set these things up and understand the parameters and the parts that you are actually setting up. The also piece of this, unlike regular IP networks, you cannot have diversity routing that is unidirectional, meaning that if I have southbound traffic going from the PTP sources at the top going down to, let's say, the bottom right-hand camera down there, the traffic going southbound and the traffic going northbound have to take the same exact route. PTP relies on the network being symmetrical. The same delay southbound as the same delay is going northbound in the system. So the BCMA runs on all devices, and it's separated out by different pieces. Priority 1 has a default value of 127. So most devices, when you get them, you power them up, they are going to start out at 127. And they will be putting out their signal saying my priority 1 is 127. And you want to turn around and change that value. You want to get it to a very low value, but something above 0, because 0 is used by several other devices in the audio world. So you want to be in control of that. You don't want something that's added to the network accidentally that turns on and comes up as a master to turn around and take over things. The centerpieces here, clock class, clock accuracy, and clock variance, will tell us what type of clock we're locked to, the accuracy of that clock, and how much that clock is moving around. Basically, it tells us the clock quality that we're locked to. Then priority 2, underneath of that, again has a default value of 127. And you, again, want to change that to a lower number. And you want to change that to an increasing order of the Grandmaster, which is going to be the lowest value. The second master in line, third, fourth, fifth, however many you have, would be increasing numbers. So the lowest value wins. If you turn around and you put in your system and all of your masters have the same priority 1 and same priority 2 numbers, they had to come up with a tiebreaker, and they typically use the MAC address to be the tiebreaker. So it takes the control out of your hands, and you really would have to go looking to figure out who your grandmaster actually is, which is not a good thing when you're doing maintenance on a network. So on sync sources, Leader's got the LT4610 sync generator, and you can set up the PTP to be in master mode. You can enable the BMCA, and you can enable the SMPTE profile. Then you can come down and set what your domain's going to be, the communication mode, which typically today is multicast. The announce intervals, you just take all of the default values, which is typically a 4 Hertz announce interval and an 8 Hertz sync interval. And then set your priority 1 and your priority 2 numbers. So in this case, I've set them to 12 for both of them. And then whether you're 1-step or 2-step operation. Typically today, we're going to be in 1-step. 2-step means you've got sync and a follow-up message, and I'll talk a little bit about that in a second. But in today's networks with today's PTP engines, we do not need to run in 2-step mode, so we actually cut down on the traffic on a network. So if we look at this particular illustration here, if you look at the sync unit on the left, priority 1 was set to 14, priority 2 was set to 26. The unit on the right, priority 1 was set to 14, but priority 2 was set to 20. If they are both locked to GPS, who's going to end up being the grandmaster in this particular situation that we have here? Since priority 2 is a lower number on the unit on the right, he is going to end up being the grandmaster. The unit on the left is just sitting there listening to the unit on the right, and as long as he is running, he's going to stay as the grandmaster, the unit on the right. But if something happens in a network, again, the unit on the right here, because of 20 versus 26 for priority 2, is going to be the grandmaster in the network. But if all of a sudden I get a degraded GPS signal, remember that the clock class sits between priority 1 and priority 2. So at first, the unit on the right is going to say, hey, I've lost GPS. I'm going into holdover, meaning I've switched to my internal oscillator that was locked to GPS, which is typically an oven-controlled crystal, so it can maintain time for quite a while. But it's going to go to a class 7 rather than a class 6. But the unit on the left is still sitting as a class 6 clock. He is going to turn around and take over as being the grandmaster, since he has a better clock than the unit on the right. So if you completely lose GPS, or if something happens to the signal from that unit into the switch, the unit on the left will take over. Now, in the case of just something happening to GPS, it's going to be a soft walk. The unit on the left is going to see that it's a higher priority from a clock class than the unit on the right. It's going to turn around and start putting out its announce messages. The unit on the right is going to see that the unit on the left is better than he is, and he's going to go into a listen only mode. But the unit on the left is still putting out the same exact time that the unit on the right was, and it just walks over. Okay, you were listening to this grandmaster, you're now listening to this grandmaster. the messages are exactly the same. If the network is disrupted, like most things, you're going to have to detect the absence of the signal. So PTP is, in fact, going to go away for whatever the cycle time has been set for. Typically, it's 3 messages, and you're going to get 3 announced messages before the unit on the left is going to say, hey, you're gone, I'm going to jump in here, and then it will jump in. All the units, the slaves that are locked to it, will still be freewheeling through what they're doing, so there shouldn't be a big disruption in what's going on, but it will have to be a resync, which is not huge, but there is a little bit of a loss in going through that. In this particular scenario, if you look, the unit on the left has a priority 1 of 13, priority 2 of 26. The unit on the right has a priority 1 of 12 with a priority 2 of 20. What's going to happen? So he is now the Grand Master because he has lower priorities than the unit on the left. But this is why you need to keep priority 1 the same. If something happens to my GPS signal, the unit on the right is still going to be the Grand Master because priority 1 trumps everything below it. And the unit on the right, even though he's on his internal crystal, is still going to stay as the Grand Master. And eventually it will start drifting a little bit to where the unit on the left is perfectly GPS locked, but because of priority 1, he's not allowed to jump in and take over. If the unit on the left was priority 1 of 12, he would have walked in as soon as he lost GPS and said, hey, I'm a better clock than you are. Start looking at me. So the only way the unit on the left is going to take over is if the signal is completely absent and there is no other Grand Master, or his priority 1 is the same, his priority 2 is better than anybody else that is on the network. But in this case, because now the GPS signal went away, now the unit on the left will take over to be the Grand Master. And this is why it's really, really important when you're doing any greenfield testing or testing your networks that you don't just yank the fiber out to look at whether I switch from my Grand Master to the second master and he becomes the Grand Master, that your switching happens. You really want to start at the GPS signal and remove the GPS signal so that both units are still there and still on the network. And the unit on the right then would be superseded by the unit on the left if priority 1s are exactly the same. You don't want to find this out in a working network that the transfer didn't happen correctly because you didn't set priority 1s correct. The other thing that you want to be aware of is just because of the volume of traffic and how fast the traffic is, it's in the gigabit range for video and in several hundred megabit range for audio, you typically cannot set QoS on the audio and video. There's RTP timestamps that will be delivered with that data. So when it's received, the buffers can put it back in perfect time. But the thing that we don't want to have happen is to have PTP come out at the wrong point in time because of what's going on in the switch. You don't want to have PTP put out at a too late a time, because then when you get the message, it's actually for a different timestamp point, and then you have to go back and try to correct for that timestamp point. You want to be able to put on QoS, and most PTP sources will put out a differentiated service code of 46 saying this is a high priority message, and it has expedited forwarding to get in front, and that way your PTP messages will stay in order and be as close as possible to the actual time in which they were actually time-stamped. So there are several PTP messages to look at things, and there are announce messages, sync messages, possibly follow-up message if you're in two-step mode, delay request and delay response messages. Now, setting up the announce message is going to go out and say, hey, I am the Grandmaster, here's my priority 1, here's my priority 2, here's my clock class. That's going to set up the BCMA. The sync message then will be the Grandmaster sending out his time to the slaves. In a two-step environment using follow-up messages, early sync units couldn't stamp the time value correct when it sent out the sync message, because it just didn't have enough CPU cycles to be able to timestamp the correct time in the sync message. So they used a follow-up message to put the correct time for the sync message in, and would send it at a fractional later point in time, so that the receiver now says, okay, this is the actual time that sync message actually was. But with today's PTP sources, we don't really need to use a follow-up message, and it's probably best not to, just to limit the amount of PTP traffic. Delay request now is a slave talking back to the Grandmaster, and it's part of the negotiation between the slave and the PTP source of getting the slave's time set exactly to the Grandmaster. So what happens here is the Grandmaster is going to put out his time as a sync message to the receiver. So the receiver on the right already knows his own time, which would be time 2. Once he receives the sync message, he knows what the Grandmaster's time is relative to his time. He is going to send out a delay request, which is going to be sending his time back to the Grandmaster. When the Grandmaster receives the delay request, he is going to send out a delay response, which is going to be his time again. So now the slave has the first Grandmaster's time, his own time sent to the, at time 3, sent to the Grandmaster, then the Grandmaster's time as a response to that message when he received that message. It's going to take T2, subtract it from T1, take T4, subtract it from T3, add those two together, divide by 2 to get what is the delay from the Grandmaster to the slave, and from the slave back to the Grandmaster. And by dividing it by 2, you get a 2-to-1 average, and get a little better average, and the slave will now know how much time to correct. Since we are syncing oscillators, it can't just yank itself to that point in time instantly. You're going to see messages come in, and it's going to slowly pull within a matter of a few seconds that time actually in. So on a waveform monitor that is now doing a bunch of IP stats as well as all of the waveform functions in the IP world, we can see that we've got T2 to T1's delta, and we've got the T4 to T3 delta. You take those two, add them together, so divide it by 2, and we get the current delta, or the current time that it takes for the messages to get from the grandmaster to the slave. So the slave now knows how much it needs to correct its time. And then it's really handy to turn around and have the minimum and the maximums of those two messages, because that will tell you when your network starts to get stressed. And you want to keep an eye on those messages, as we'll see in just a second. So from a graphical point of view, when you send out multicast messages go out to all receivers that are joined to that multicast. Every receiver that gets on the network automatically joins the PTP messages. So you're going to send out an announce message saying, I am the master, this is who I am, it's my IP address, this is my MAC address, this is my priority 1, my priority 2, my clock class. And that's going to go out to all the slaves that you can see down on the bottom. It will send now out its sync message, which is, hey, this is my time. Send out that time. All the receivers on the bottom see that. If you're in a 2-step mode, you'll send out follow-up message to restamp what the sync time was. But then one of the receivers is going to send out a delay request. It says, okay, Grandmaster, I got your time. Here is my time. And ask for a delay response to be sent to that one receiver. But since it's a multicast message, just like when the slave sent out his response to the Grandmaster, it went to all the slaves, but they ignored it because it wasn't for them. It was for the Grandmaster. But now the delay response from the Grandmaster gets sent to everybody, but it's only for the slave, in this case on the far right. So there's a lot of traffic going back and forth on the network for PTP. It's moderately verbose. There is a mode called mixed mode, and mixed mode sets up that the messages from the Grandmaster, the announce message, and the sync messages are all sent out as multicast. But the delay messages are all sent as unicast, 1-to-1, and it actually makes the loading on the network a lot less. So I am going to send out the announce message saying, I am the Grandmaster. Here's my ID, here's my clock class, my priority 1, priority 2, to everybody. He's going to send out his time as a sync message. Send out follow-up if you're 2-step. The delay request now from the slave is going to be a unicast message to that particular Grandmaster. The delay response now from the Grandmaster will be a unicast message just to that one slave. So the loading on the switch from PTP messages is a lot less because you aren't sending all that multicast to everybody. But with today's network and using boundary clocks have pretty much done away with the need to really do mixed mode. And there's a lot of devices out there that can't handle mixed mode correctly. It doesn't always work on all devices. Multicast will work every single time that you have a device that is working. Mixed mode may or may not work. I've seen a lot of cases where devices don't do mixed mode correctly. So if we kind of look at the messaging going through here with transparent clocks and boundary clocks and the slaves, the Grandmaster at the top, in this case of the Amber network, is going to be sending out his PTP messages. He hits a transparent clock. In the case of a transparent clock, when he passes that messaging out, he's going to put a correction factor in there to tell the slaves or tell anybody else that's locked to him, this is how long PTP took to get through me, so that they know how much to remove that time. And then we've got boundary clocks on the bottom, which is pretty much all that's used in today's world. The boundary clock regenerates, like I said, it's like a reclocking DA. It's going to regenerate its own brand new PTP messages on a port by port by port basis. It is locked to the Grandmaster, so the Grandmaster's time and the Grandmaster's announced messages will pass through the system. But the communication for delay request, delay response, all of the syncing will be done just from that boundary clock out to the individual sync messages, out to the slaves that are out in the network. And then the secondary PTP device will be listening to all the messaging that the Grandmaster is putting out to know when he should step in or shouldn't, and the pecking order of who does what when. There is also, in a lot of cases, a lot of spine leaf networks going out. Spine leafs are really good when you have a lot of messaging going from leaf to leaf, is where they work really, really well in the message loading. That's where things go. And if you think about it, a video network, typically outside of a spine going to somewhere else, it's typically only feeding the leaves in a video network. It's not feeding an extended network outside of that typically. So it works really, really well then to have all of your leaves that are connected to all of the spines, and we can turn around and have a lot of messaging. You just have to make sure that you do have the proper messaging from who's going to be the Grandmaster to the secondary master. So sometimes you'll have a link between the two spines that is just a PTP only link, so that those two can communicate and allow the two Grandmasters, so the Grandmasters don't have to go all the way down to a leaf and have one of the leaves pass the messaging back and forth between everybody. So let's take a quick look here at the different tools that are out there. So like we mentioned, we've got the sync generator and the different things that you can do with the sync generator. It still provides all the black burst, tri-level, SDI signals, AES signals, word clock, but it also has the ability now to put out PTP and be locked to the satellite and be able to be locked to GPS. On the status page, it tells you how everything is behaving within that unit. And if you look in the top left-hand side up here, it's going to tell you how many satellites you're currently viewing, what the carrier to noise is of the signal you're receiving, and then all of the GPS status. And everybody should be normal as we walk through all of this. Down on the bottom right-hand side, then, is the actual PTP messaging going on. The enabled master, what domain you're putting out, what profile type, in this case 2059 for video, then what clock class. Clock class 6 says you are GPS, the clock accuracy of that, and then all of the local offsets. So the clock class, the typical clock classes you'll see out there are generally 6, 7, and then 248. So 6 is saying, yes, I am locked to GPS. If we lose GPS, you'll go to holdover and you'll be a clock class 7. But if the secondary unit is still clock class 6, he's still locked to GPS, that's when the BMCA is going to take over, and the other unit then is going to turn around and become the Grandmaster. The 248 is also known typically as handset, or you're running on the internal oscillator. So if you lose GPS, you will go to clock class 7. At some point when the drift time becomes too large, you will start going down to a lower and lower clock class and end up at a 248, which means I'm running on my internal oven-controlled crystal in all of this. So let's see if we can pop over and take a quick peek at this. As soon as I find him. Okay, something happened here. Welcome to live.
Thanks everybody for all your questions, and you can keep those coming in. And when we get toward the end, we'll give those to Steve, and he can run through all the great things you've been asking about. So thank you. If anybody wants a demo of the LV 7600 or any of the things that Steve's been going over, just shoot me a message in the chat, and we'll set it up for you. Or if you need technical information as well, we can come back to you with that.
Okay, so now this is the LT 4610 that I have running here. This is my Grandmaster. And you can see up here on the top, the GPS is locked. Everything is normal. Down on the bottom right-hand side is all the status for the PTP. And up on the tabs, you can set up your PTP. There's 2 PTP generators. I can enable the master, enable the MCA on it, set the profile. So we can be 2059 or AES67 or just 1588. And then the detail settings where you're going to set your domain, which you want to move off of 127 and set it to some number that all your PTP devices are going to be. Your communication mode, the normal announced and sync intervals are going to be the defaults, which is going to be 4 Hertz for announce, 8 Hertz for all the sync messaging, and then the priority 1 and priority 2 messages. It may kind of seem counterintuitive to set priority 1s the same, but that's what's going to set you all up in the same group as far as looking now at the clock class and priority 2s underneath of that in order to turn around and walk over and look at things. You can still set up your gen lock. Who am I locked to? In this case, I am currently locked to GPS. I have a GPS antenna about 10 feet away from me here, locking the system. And you still have the ability to set up all the black sources, the SDI sources, and everything else that you would associate with a normal sync pulse generator, and be able to monitor the status, set up alarming as either SNMP traps or GPI messages coming off of the unit itself. So if we look here at the messaging going on, so now I am on the 5600 looking at the messages going out, and we will look at this in more detail in just a little bit. But you can see at the top of the screen up here, it is telling me the Grandmaster ID, which is its MAC address. So really all we need to look at is this last octet. This guy is B8, and that's who my Grandmaster is. And then what domain it is that I am sending out, and then my lock ability to that current messaging of what we actually have going on here. And we'll look into this in more detail in just a little bit. So on the unit itself, looking at the either 7600 to 5600, we do have several displays that I'll talk about here. If, like I said, you see at the top of the screen, it's going to tell you who the Grandmaster is. The right-hand side is going to tell you the times, the T2 minus T1, the T4 minus T3 times, what the current is, what the min and max is of what you're going through. Then right below that is all the announced intervals. And we get the network delay through the BMCA math, which is subtracting T2 minus T1, subtracting T4 minus T3, taking that, adding it together, dividing it by 2, and that's what you're seeing the result of in the graph that's going across. So it's going to tell you how much network delay you happen to have in your system. Now, it's really, really handy to be able to look at that network delays because of something like this that might happen. In this case, this was a drop of GPS signal that actually dropped for more than 30 seconds and was lost and then came back. And if you look at the minimum number over on the right, it is telling you, hey, the time did go to 0 on you. So if you have a disruption in your network, it's very helpful to be able to use these charts and expand the time. As you can see, the timeline can go from 2 minutes out to 72 hours. So it gives you quite a bit of time to be able to look at and see when you actually had that disturbance on your network and help you hopefully be able to troubleshoot it and go through things. You also might have problems where just things get really hairy. In this case, if you look at both min and max, signal dropped out for a substantial amount of time and then ended up coming back and came back. And it's not that uncommon when the signal is coming back in to get time swings as things move in and start to lock. But those min and max numbers on the right-hand side when you're monitoring PTP can be a godsend to you. The last SMPTE conference that went out, one of the gentlemen that was given the conference was talking about PTP, and he said the best thing you can do to PTP is monitor it, monitor it, and monitor it. Here is a network that is fairly stressed. You don't want to see this type of time jumping around in your network. Most slaves use what they kind of call the lucky packet algorithm. So if there is a few packets that are outliers, it'll turn around and not look at them and try to get the main packets that are giving you a much cleaner time base. But if every packet ends up being an outlier and they're jumping around all over the place, this can cause you to drop lock in certain devices as we go through. This is really what your network for PTP should look like on a very high class switch. So if you're using really big iron and very high end switches in your network, your PTP should have very little movement in it and should look very consistent and very, very clean. You don't want to get to a case where you're getting your PTP looking like this, because it's just like black and tri-level. It is the heart of the system and everything's going to be trying to lock to it. We can also look at the graph from a slightly different perspective. Rather than looking at it from a delay, a network delay perspective, we can look at it from a time perspective. If we change the math to subtract the two values of T2 minus T1, T4 minus T3, it gives us a time perspective. And just like time perspective, you can actually see when things are syncing. So this was when I started up my system, put it on time, and before PTP completely locked, you could actually see the receiver dialing in its time and looking at the time values and bringing it in to absolute lock as it's changing its oscillator. And like I said, this is going to look very much like an analog PLL or even a digital PLL, that it's going to turn around, take those values, hone in, and then finally lock itself, because you are locking an oscillator. So it can't just take a digital value and say, hey, I'm this time now, as we go through things. So if we walk over and take a quick look here at what we are looking at, you can see that I've got my PTP messaging going across here. There is a little bit of movement in that PTP messaging. This is probably not what you'd want to see out in yours. I'm just using a simple little office switch, which knows nothing about any QoS or anything else. And I actually have video running on here. So if you look, there is actually 2110 going across this. And with this particular business class switch, instead of a big piece of iron, it is getting in the middle of PTP slightly and giving me some variance. But you can see that the variance is still less than half a microsecond, going out just right at about a half a microsecond. And we can change the values. I can change to look at the time offset. And in this case, the time offset is going to be very indicative of what the delay network is in this case. Just because when the packets are moving, they're changing the amount of time, and we can go through that. I can look at the chart, like I said, from 2 minutes on out to 72 hours and look at different things. If you notice at the top of the screen up there, I am locked on the Grandmaster B8. I am going to try something here live, and we never know exactly how that's going to work, but it should work. I just disconnected the GPS from that particular unit. It is going to end up going to internal fallback. It's going to go to a clock class 7. Once it gets done with its clock class 7, the second unit is going to turn around and say, hey, and there it is. It just went to B1 from B8, and you can see a little spike when it changed, but not much. But now we're on B1. So the secondary unit walked in, took over, and virtually no disruption in time. And if you look at the max here, it's not even a microsecond difference, and it's only one hit, which a receiver would turn around and ignore, and it just keeps right on going. If I turn around and deload my system, I'm going to remove the video off of my system. So you see it go to no signal up there at the top, but PTP is still running. You'll now see that my network only, or my little network switch here, only has to contend with PTP, and it's really happy just contending with only PTP. And if we go back and look at, you can see that my 4610, my sync generator, is in stay sync mode, which means it's keeping the oscillator in the exact phase, exactly where it was. But it's now in clock class 7, which is now GPS holdover down here in the bottom. And looking at things, still on domain 44 and clock class 7, and now it's out to 25 microseconds rather than 100 nanoseconds for accuracy. Handset just means you're on the internal oscillator. and it would turn around and take it just a little bit to turn around and relock itself as it starts to regain the receiver. Now it sees 10 out of 15 satellites, and it's starting to pull itself back into lock. When it fully locks, then it'll go from clock class 7 to clock class 6 and take back over as being the Grandmaster again as time goes on. Okay, I got to keep going on this or we'll never get done. So the other thing that we have that everybody wants to know is, where is PTP relative to the rest of my house, i.e. where is it relative to black burst or tri-level? And we can look at those things. And if we look at PTP versus RTP, PTP is going to have the same time point that we have for black burst. So PTP is going to start at the same point in time, but RTP is going to start at the first line of video right at the top left corner of that green. So in a perfect world, a 1080 signal would be delayed by 21 lines, which is the vertical interval, and about 4.152 microseconds. In the real world here, depending on how you count, in this case, it says we're on line 20, so we are 21 lines out because it starts at line 0. But you can see the reference is PTP to RTP, and it shows the 21 line offset. The horizontal time is never going to be absolutely perfect. It's going to wander just a little bit because you're getting slightly different correction values, and it's going to move left and right just a little bit on you all the time. If I change it from looking at where is PTP relative to black burst, in this case, it says they are perfectly lined up with each other. Exactly what you want to have so that your video, when you deal with a house that's dealing with some SDI, some IP, everything is going to be perfectly in line with each other. And it's going to look exactly how you want, and switching from an IP source to a black burst source is going to be straight. Looking at domains, like I said, you can run multiple domains. The priority 1, priority 2s can be exactly the same, but the domain number is going to keep them different than each other. The unit on the right is doing my video. The unit on the left, in this case, is doing the audio, and it's domain 0. It's going out, locking my Dante in this case. The unit on the right is priority 3, and all devices that are video and looking at domain 3 will lock to him, and you'll go through all the same stuff for priority 1, priority 2, and the rest of the world. In a network, running short here, so I'm going to go through some of this really quick. Sorry, guys. We need to go through some of this real quick. PTP is going out from the ground master to everybody. The control, NMOS, the audio video is going across the network and going out to the world here. You'll have a secondary unit going on. In troubleshooting PTP, one of the biggest things is check your priority 1s, your priority 2s. Make sure priority 1s are set to the same values for all PTP sources. Priority 2 are set in ascending order from who you want to be the grandmaster to the secondary master on up. Make sure you are on the same domain, and make sure there's not a second PTP source set to the same values, where you're going to get into a fighting war and you're going to have to rely on the Mac to set it, and have a second generator out there. That's why you want to use very low numbers for priority 1 and priority 2 here, and also make sure the asymmetry of the network is exactly the same.
Cindy.
We'll look at
Steve,
some
that was
questions here.
wonderful. Most excellent. So some questions from people. What priority would you recommend the master should be set to based off the 0 to 127 range? And what are the devices that you'd potentially set up to 0?
0 is audio. So it's AES 67, and anybody that's going to be using AES 67 is going to be on 0. You want to set somewhere, I use something in like the 3 to 10 type range typically for priority 1, but something that's a low number. There is no exact. It's your network. You're going to set it up how you want it to be. But you just want to get off of 127 so that a rogue device that gets put into the network that you're building out that decides to be a grandmaster, you don't get in a fighting war there.
So then when you split your grandmaster for audio and then for video, that would assume that you'd have a secondary for each. Is that right? 2 for video and 2 for audio?
Yes, and a lot of the PTP sources, as well as the LT4610, actually can be 2 PTP sources. So as long as they're on different domains. So it can be a video PTP source and an audio PTP source at the same time, putting out just 2 different domains. But it will still, they're both going to walk at the same time since they're locked to the same GPS signal. But most of the sources out there can actually put out 2 different PTP signals so that you can lock all of your AES 67 devices and all your video devices correctly off of one unit, and then have a secondary unit that would walk in and would actually change both of those 2 over to the secondary unit on a GPS or a SVG fault.
Okay, and then there was a comment sort of around those settings, around the priorities, that setting both priority 1 and 2 to 12 felt counterintuitive. Wondered if you had a comment on that.
It's just 2 numbers I chose. It's, like I said, the 2 low numbers, as long as my priority 2s are ascending numbers, they can be any number you want. Like I said, the defaults are 127 for all of them. So I just chose 12 to be my starting point. And then I took priority 2. I made my secondary unit priority 2. It happened to jump up by 2, so it was 14. So
that makes sense. That makes sense. Now, how is the catch-up or resync rate when things are out of sync? I think this is right when you were talking about spine leaf or right before that.
Yeah, so a device syncing, the SMPTE says you're supposed to be able to sync within 8 seconds. Some devices will do that, some devices won't, because you really don't want the time to be too short, because then you're going to be pulling your oscillator all over the place if you have network variations. So you want a little bit of a long time constant in there so that if you do get a couple packets that get really out of skew, your time constant will kind of level that out. So it's going to vary on a slave device by slave device how long it's going to take to sync itself.
We've got several questions on a theme here that are really, what if you can't get a GPS signal? How much does running the internal clock effect or internal effect clock quality, and sort of what to do if there's no GPS available? Maybe an example with the mobile unit. Yeah,
it's not an issue. It's a crystal controlled clock, and it will be absolutely perfect. It's the same as taking black when you can't GPS black. There is no difference. It's going to run on the crystal controlled oscillator, and everything's going to run absolutely perfect. I do it in my office here all the time. I don't break out my GPS antenna most of the time. I run it on internal.
Okay, and so related to that, someone was asking, what do you recommend as the best practice when the PTP Grandmaster has to be referenced to incoming blackburst?
Okay, for that, you actually, believe it or not, you want to reference it to PAL and with time code. You want LTC in it. The reason referencing it to PAL is there's no drop frame. you don't have to do the calculations for the 0.001 offset. So PAL is an integer-based system, so that your time is going to be absolutely perfect. And then time code inside of there is going to give you the time. And that's the best thing to lock to if you can. And then you don't end up with that every 12 frame type jump, and then all of the rest of the calculations you have to correct for the 0.001 offset.
Okay, so PAL, because there's no drop frame. That's great.
Yeah.
All right. And so can a PTP system work with a single grandmaster and a non-redundancy switch topology, no BMCA?
It works perfect. There's just no backup. If you lose the grandmaster, it's like, blackburst. Think of blackburst. If you only have one blackburst source, you lose it. You don't have any sync in your house. If you lose your PTP source, you only have one, you have no sync in your house.
Okay. And a question now on the difference between the ST2059 profile and the general profile. What's the difference there?
General is just 1588. You have none of the fields that I looked at in the presentation.
Okay.
So you don't have any of the empty fields. It doesn't know anything about frames, doesn't know anything about time code, anything else, 10 frame sequence, where does the frame start? It'll still know where frames start and where frames end based on counting, and it knows, okay, I'm set to 2398. Okay, I can calculate out, here's the start of a frame, here's what line I should be on. But the rest of the data that's not in there that we want to be able to send across the system isn't there.
All right. And then can you use NTP instead of GPS?
No. It's Blackburst is more accurate than even NTP. So PTP is the hardware cousin to NTP, which NTP is a software architecture, where PTP is a hardware architecture. So it'd be better to use almost all PTP sync generators can be NTP sources because they are GPS locked. But Blackburst would be a better choice than probably NTP, just because it's coming across the network.
Now, in looking at the LT4610, can that sync to PTP that's generated by another grandmaster in a different truck?
Yes, it can. Does it absolutely perfect.
Oh, good. Okay. And then a question around AES67. What if you want your AES67 devices to provide the ST2110-30 to be added back into the ST2110 video? We can.
I'm gonna have to canoodle on that one for a minute.
Yeah,
So
I was thinking.
we'll get to that one offline. I'm not sure.
Yeah, I just realized that's a circle back one. So we'll
Yeah.
get back to you on that.
Sorry.
Yeah, I just have a final one here, and wondering if you could give advice on what features or specs to look for in switches to use here.
The biggest thing is you want enterprise class switches that know about PTP, but know about the SMPTE profile, not just 1588. They need to know that they can work on 2059-2-1-2. So that's the biggest thing to look for.
Wonderful. And for all of the other questions, we'll circle back to you. I think that's great, Steve. Thank you.
Sorry I ran over a little bit, guys, but if you've had any of my other seminars, it's not uncommon. So I'm sorry.
Steve's contact info is in the chat, as well as Pete and Scott's contact info. You can reach out to them for further information, to get a demo, to get technical details. Thank you.
Thank you, guys. Have a great rest of your day, folks, and stay safe.